Evening, everyone. Let's see here. Any news? Had a division meeting on Friday and don't expect to be going back in the spring. But you never know. And let's see, what else did I hear that was interesting? Not a lot. Okay, so there was a few people that wanted to see a couple of these exam questions done. So let's do that before we get started on today's stuff. And okay, so here we go. And flip this guy over. All right, so there's an issue. It was an issue with find the area of the surface. You take y equals, now it's this funky function. It's a indefinite, or it's a kind of a indefinite interval, sort of, minus 1 dt. Okay. Now you want to revolve this about the y-axis. Revolve about the y-axis. Hold on a second. Okay, so now the confusion, I think, came in with what you're supposed to do, okay? So the formula that is the area is the integral over some interval of 2 pi, and then when you go around the y-axis, it's the opposite letter ds, okay? The bounds that they gave us is right here, 1 to 16. Okay, so we're going to do a dx integral, okay? So now it's going to be the integral from 1 to 16 of 2 pi x, and then the square root of 1 plus dy dx squared dx. Write that guy better. dy dx squared. Okay, so fundamental theorem of calculus says that y prime is going to be the square root of the square root of x. It's not really sensitive today. This is excuse me, pretty gonna sleep talk. Square root of x minus 1. 1 plus y prime squared is equal to 1 plus this thing squared. So it's 1 plus the square root of x minus 1, which is just radical x. So if you plug this into the formula, it's going to be the integral from 1 to 16, 2 pi x. Okay, remember the x stays because dx integral. If we were doing a dy integral, we would have to invert this up here and solve for y in terms of x. Now, that's not the easiest thing to do in the world. That's called a Fourier inversion. Some of you will learn about that later. Okay, and then we have the square root of underneath there the square root of x dx. So that's going to be 2 pi integral from 1 to 16, and then it's going to be x times x to the 1/4 power, square root of the square root of x, okay, dx. So that's going to be 2 pi integral 1 to 16 x to the 5/4 dx. So that's going to be 2 pi times x to the 9/4 divided by 9/4, evaluated at 1 and at 16. And so that's going to be 8 pi over 9 times the 4th root of 16 is 2. Raise that to the 2 to the 9th power. Then we're going to subtract off a 1. And just to finish it off, that's going to be 511. And then for you guys that multiply the whole thing out, 8 pi over 9. Okay. So for those of you that were curious about this problem, are there any questions about it? One of you sent me something like you had put it in a program or something, and it had done the same exact thing that your friend did or whatever like that. I don't know, some story going on like that. But it seems like you weren't answering the correct question. Like instead of finding the area, I think if I'm going to guess, I bet you it's the arc length. Okay, so let's see if we could work out the arc length. Okay, so again, the y is equal to the 1 to x, and then it's square root of t minus 1. I think I know what's wrong with this pencil. I think I need to set it up. There's some kind of way I'll fuck with it later. Okay, and remember we had that the ds thing ended up being the square root of x dx. Okay, remember that was dy dx. Okay, whoops, that's not dy dx. This is dy dx. Okay, and then the ds piece is this part. So now the length of the curve would be the integral from 1 to 16, and then it's going to be the 1 plus dy dx squared dx, which is the integral from 1 to 16 of the square root of x dx. 1 to 16, x to the 1/4 dx. So this goes to x to the 5/4 divided by 5/4, evaluated at 1 and 16. So that's 4/5. And then this is going to be the 4th root of 16 is 2. 2 to the 5th power is 32 minus 1, which is 4 times 31 over 5, which is the most popular incorrect answer. Okay. All right. So Anybody out there? Or am I talking to myself?
And they're asking about 7 and 9.
Okay. I'll be doing 7 and 9 as well. Okay. But did any of you realize that this problem is in the book?
Yeah, but I didn't even think to look that for this answer. Like,
and it's an odd. It's odd.
It's one of the odd problems.
Yeah, it's in the chapter review. I did this on purpose. I wanted to see, you know.
I usually go through the examples. I kind of don't look to see if the problem's actually in the thing. Sometimes you put an example, like a problem that's in the example, and I'm like, oh, cool. And then I think one time you actually put one that was on the notes, which was great, but it was like the notes from like last semester.
Math 30, my Math 30 people, they're so helpless.
Oh, really?
I put problems on the exam that I did the day before as an example. And they got all into it and asked questions, and then they all miss it the next day.
Oh,
like I went on this group chat with a bunch of us in the department, and I'm like, these Math 30 people, they're not only not good at math, they're not good at cheating, you know? Because I mean, the 10 questions and the average score is like 6.5 right. You know, like I wish they would try to look stuff up. Okay, now the other thing that caught my attention about this problem is that this is one of the few mistakes in Stewart. Okay, in the question he asks for find the surface area. What he reports as the answer is the arc length. Okay, so now this is the fourth mistake that I know of in Stewart. Now I don't know if it's been fixed. I have the newest edition down here. I just don't want to open it because it's, you know, not a book. But anyway, okay.
So this would technically be the answer that they would be looking for in the book based on what they asked for, right?
See, what I was trying to see was that maybe, because I don't know how organized you guys are. Maybe, you know, like someone whose job it is to scour the textbook to see if any of Bobby's questions are in the book. Maybe that's somebody has that job. I was curious to see if guys would find it and then not even do it and just report the wrong answer. Okay. And I mean, a couple people reported different answers. Then I didn't see a lot of 124/5. I'm going to go back and look again.
I think we all tried. I mean, from what I saw in the commentary on the thing that what's his face, Brian added me to. I saw people really trying, and some of them would ask me how to do some stuff. Some of them didn't, which is okay. This one, they kept trying and getting different answers. And I literally was like, okay, you guys, one of you guys has it right. And then they're like, but which one? I'm like, it's not the arc length. He doesn't want a fraction. He would never give you a fraction. It's going to be something with a real number, like the actual. And then when I saw it, I'm like, it's this one.
Okay, this problem, I think I made it up myself. I'm gonna have to verify. I know number nine I made up by myself.
You did a good job. That one took me forever to get through. And then I didn't even, when I got to the end of it, I wanted to factor out the 2 to shorten the what's it called? The length, LNs, the natural logs. But
yeah, I'm going to go through that after I finish this problem. I'm going to go through all of those logs of the square root thing. Okay, so this derivative is 1 over the sine of x over 2 times the derivative of the sine of x over 2, which is 1/2 times the cosine of x over 2, which is the cotangent of x over 2. Okay. And 1 plus y prime squared is 1 plus cotangent squared of x over 2. Okay, now sine squared plus cosine squared equals 1. So if you divide everything by sine, 1 plus cotan squared equals cosecant squared. So this is cosecant squared of x over 2. So that means our length is going to be the integral from pi over 3 to pi square root of cosecant squared of x over 2 dx. Okay? Okay, now remember that the x is running from pi over 3 to pi. So that would mean that x over 2 is going to run between pi over 6 and pi over 2. Okay, now the cosecant is 1 over the sine, right? And in the first quadrant, the sign is positive. You know, we're going from pi over 6. Anyways, the sign is positive. So we're okay with doing this. Pi over 3 to pi cosecant of x over 2 dx. Okay, now the antiderivative of this, what I'm going to do is I'm going to let u be x over 2. This is exactly what I did when I made the key. Okay, because I don't like making mistakes. Okay, anyways, so now 2u is equal to x. So dx equals 2 du. So when I plug this in, now the u is going to go from pi over 6 to pi over 2, and it's the cosecant of u du. And there's a 2 in here somewhere. Okay. Okay, so now the antiderivative of this, I still have it somewhere on my papers here. Let me see. It's like cotangent, it's like the log of cotangent minus cosecant. There it is. So this is 2 times the natural log of cosecant of u minus the cotangent of u, evaluated at pi over 6 and pi over 2. Okay, so now I'm going to switch everything to sine and cosine because I understand those better. 2 natural log of 1 over the sine of u minus the cosine of u over the sine of u, evaluated at pi over 6, pi over 2. Okay, so this is going to be 2 times the natural log of 1 minus 0 minus the natural log of the sine of pi over 6 is 1/2. So that means 1 over the sine of pi over 6 is 2, minus the cosine of this is radical 3 over 2. The sine of that is 1/2. Okay. So now it's going to be a 2 times a 0 minus the natural log of 2 minus radical 3, which is equal to 2 negative 2 natural log of 2 minus radical 3. Okay, now when I did this, I realized I'm trying to find a length here, and it looks like my answer might be negative. But 2 is larger than the square root of 3, okay? So this is one way to write the answer. Another way to write the answer would be to write it as the natural log of 1 over 2 minus radical 3 squared. Okay. Another way you could write it would be a 2 times the natural log of 1 over 2 minus radical 3. Okay. And then do it all in your calculator, and you see that you do get a positive number, so it actually works out. Okay, so for number 9, what I did, hold on a second, let me do something. Okay, so number 9, we're looking for the length, all right? So I got y equals e to the x over 2. 1 plus y prime squared is going to be 1 plus 1 over 4 e to the x, because y prime is going to be 1/2 e to the x over 2. And if I square that, that's what I end up with. So the length is going to be the integral from the natural log of 4, natural log of 8, square root of 1 plus 1 over 4 e to the x dx. All right. So now I'm going to let u be the entire radical. I would imagine step 1, you would have let u be what's under the radical. And if that doesn't work, step 2 is let u be the entire radical. Okay. So that means that u squared is going to be 1 plus 1 over 4 e to the x. So 1 over 4 e to the x is equal to u squared minus 1. So the e to the x is equal to 4 u squared minus 1. Okay, and so x is going to be the natural log of 4 times, maybe let's since I'm going to take this. So it's going to be 4u squared minus 1. I mean minus 4. Okay. Dx now is going to be 1 over 4u squared minus 4 times the derivative of the downstairs, which is going to be 8u. Okay. And when x is the natural log of 4, e to the x is 4. 1/4 times 4 is 1. So u is the square root of 2. When x is the natural log of 8, the u is 1/4 of 8, which is 2 plus 1 is 3. Okay, so now my length is an entirely u integral, okay? And then it's going to be u times this dx thing, which is 8u over 4u squared minus 4 du. Do some canceling here, and we're going to end up with the integral from radical 2 to radical 3. And it's going to be 2u squared in the top. And in the bottom, it's going to be u squared minus 1. Okay. Now you need to long divide. Two u squared minus 2. Do the subtraction, you get 2. There's nothing left to do. So now it's going to be the integral from the square root of 2 to the square root of 3 of the quotient, which is 2, plus the remainder piece, 2 over u squared minus 1. Okay. All right, now I've done that partial fraction decomposition so many times that I know it in my heart, by heart. U minus 1 over u plus 1 du. Okay. Integrate the whole thing. 2u plus the log of u minus 1 over u plus 1, evaluated at radical 2 and radical 3. Okay, so this guy is going to be 2 times radical 3 minus radical 2. So there's that piece. And then this is going to be the log of radical 3 minus 1 over radical 3 plus 1 minus the log of radical 2 minus 1 over radical 2 plus 1. Okay. Okay, now from here, this is where I might think there might be some issues. So one thing that maybe some people did was start doing this stuff. Okay. Radical 3 minus 1, radical 3 minus 1. So that's going to be 3 minus 2 radical 3 plus 1 divided by 2, I guess. And so that's going to be 4 minus 2 radical 3 over 2, 2 minus radical 3, maybe. Okay. And the square root of 2 minus 1 over the square root of 2 plus 1, we could get, we go square root of 2 minus 1 minus 1. Top is 2 minus 2 radical 2 plus 1 divided by 2 minus 1, which is a 1, which is going to be a 3 minus a 2 radical 2. So I guess one could say the answer is 2 radical 3 minus 2 radical 2 plus the log of 2 minus radical 3 minus 3 minus 2 radical 2. Now I did a whole bunch of stuff with this. I also divided, like I flipped this thing over and multiplied. Okay, so a few of you think you got this right. Now I just didn't want to work through. See, there's no work for me to do, to look through, you know, like this integral right here. if you feed this integral into a software package, it might spit out hyperbolics. Okay. So, and I did see some people, well, it's been my experience in the past that usually about maybe 10% of the class will do hyperbolic stuff with this. The rest just does partial fractions. Okay, so if you still think that you have it right, then wait till the end of class. But take your answers, see if you can manipulate my answer into yours. Okay. I looked at a few of them and it just didn't seem like the numbers were there. And but anyway. Okay. All right, and of course, number 10 was an elliptic integral. Okay. Okay, so let's start back today with sequences and series. I think this week I'll give you the test on like Wednesday, or maybe even, you know what? I'm going to do the test on Thursday.
Oh,
that
okay.
way I'll have more sequence and series stuff I can get out of the way. And I've always been planning on splitting this test up anyway. Maybe this is, kind of good. All right. Okay. So sequences and series. All right. So we had a sequence of numbers, AN, and, we start our counter with 0 normally at this level, and where it's an infinitely long sequence. Okay. So for example, it might be, something like A sub n is equal to 1 over n. So now you have to start it at 1. Okay. So 1, a half, a third, fourth. Okay. Now, if this was a big result for us, if AN is equal to F of n, and if the limit as x tends to infinity of f of x is equal to L, then the limit as n tends to infinity of AN is also going to equal L. Okay, this was a big result for us. This means that we can use all of the limit results, squeeze theorem, L'Hopital, all of that kind of stuff. Okay. And we had a real curious result that said, okay, any bounded monotone sequence will have a limit. Okay, that was required us to use the completeness axiom for that guy. Get these papers out of the way here. All right. Okay, so, for example, the limit as n tends to infinity of n over n plus 1 is equal to 1. Whether you want to use L'Hopital's rule or something else, that's what we get. Okay. And there were some special results that I wanted you guys to remember. Because they're going to be coming up next week. The limit as n tends to infinity of 1 plus 1 over n raised to the nth power is e. And the limit as n tends to infinity of the nth root of n is equal to 1. So these are some results that we might possibly need here in our future. Okay. Okay, now, when we talk about series, what it is the sum of a sequence, AK. Now, this could be finite or infinite. Okay, now we beat to death with a stick the finite case. Okay, that was back in pre-calculus. We had our arithmetic sequences and our arithmetic series. We had a geometric result. Okay, so this series, this infinitely long series, might converge or not. Okay, so the question, well, before we do that, we have to write down what we mean by an infinite series. So when we write down an infinite series, k equaling n to infinity of ak. Now I do this a lot. I start the counter, wacky all over the place. Okay. A sub k is equal to the limit as n tends to infinity of the sum. K starts at n and goes up to n of the ak. Okay, so this was our prototype of how to make this work. Okay, so we call Sn, which is going to be the sum, k starting at some number, I, and going up to n of this a sub k, is called the nth partial sum. So that thing is called the nth partial sum. And so from this, we get a new sequence. It's the sequence of nth partial sums. Okay? And so the way we're going to decide if the infinite sum converges or not, we say if the limit as n tends to infinity of s sub n is equal to s, then we're going to say that the sum k equaling, I to infinity, as long as we're starting at the same spot here, okay, of the AK converges. Now, in this case, to S. But most of the time, we're not really going to be interested on whether or not something adds up. I mean, what it adds up to. We just want to know if it adds up to something. Okay. Okay, so for right now, for our sequences, we're assuming now that the AKs are all positives, okay? And that we're adding up lists of, these guys, okay? All right, so a result that we have, and this goes all the way back to pre-calculus, and for that matter, even intermediate algebra for some of you, if we were to add up from 0 to infinity, x to the k, it's going to end up having this closed form, provided that this x thing is less than 1. Now, you're accustomed to seeing that as an r, okay, but we're going to start using x's. Okay. And this is the result that we kind of snuck that idea out of. All right. And so we start thinking about things like, what conditions must the sequence A sub n satisfy so that the sum, the infinite sum of the ANs adds up to something. Less than infinity means finite. Okay? And we arrived at a result that was a necessary but not sufficient condition if the sum k equaling m to infinity of the AK, okay, if this thing converges, then we established that the limit as k tends to infinity of the things that we're adding up have to go to 0. Okay. Now, this is a standard type question I put on exams just to see people know what they're doing. Okay. N equals 27 to infinity. And I'm going to go 3n squared plus 2 divided by 4n squared minus n plus 65. Converge or diverge? Okay, so the solution here, this an that we're adding up is 3n squared plus 2 divided by 4n squared minus n plus 65. So somebody tell me what the limit is as n tends to infinity of the ANs.
Infinity. By infinity.
Look, it's 3n squared over 4n squared.
Three-fourths.
Yep. 3/4. That does not equal 0. So this means that the sum from n equaling any number, who cares, 27 to infinity, of the an equals positive infinity, or it diverges. Okay? Now, what'll happen on the exam, and it's usually number 1 on the test, I just, get your feet wet. I say, does this converge or diverge? And people say, an is this, the limit of the an is 3/4. Now, there's going to be some condition that later on in another test where if some limit is less than 1, something happens, and if something is bigger than 1, something different happens. So people look at this, we've already done the ratio test, and you think, oh, 3/4, well, that's less than 1 converge. No, this diverges because the things that you're adding up aren't going to 0. It's basically you're trying to add up an infinite number of 3/4 or 3/4, which is going to be, not happening. Okay, now it turns out that this is not sufficient. Okay, so definition. The series given by the sum from 1 to infinity of 1 over n is called the harmonic series. Okay, and what it is, it's 1 plus a half plus a third plus a fourth, on and on. Okay. Now, the result that we established last time, and this is by a guy D or Simi, 1300s, figured out that if we were to add up the harmonic series, you get that. And I haven't seen his original paper, but what I've read about it is that he basically proved it the way we proved it. You know, we got the nth partial sum to be bigger than a fixed number involving n, and then when you let it off to infinity, it get pushed off to infinity. Okay, so the harmonic series diverges. Okay. So apparently these numbers don't get small enough, you know, to add up to something. Okay, so this is our prototype of a diverging series that had a chance to converge. You know, if I gave us this series like here, the sum n equal 1 to infinity of n squared, that never has a chance to add up, right? Because you're adding up 1, 4, 9, that's going up to infinity. This guy at least had a chance, okay, but it didn't work out. Okay, so that's a result that we're going to want to remember for quite some time. Okay, and let's see, what else do we want to talk about in here? Okay, so we've got a handful of results. Now, these are all predicated on the hypothesis being satisfied. Okay, so this starts to become important. Suppose that the sum of the ANs, sum of the BNs are converging. Converging series. The AN is bigger than or equal to 0 and the BN bigger than or equal to 0. We're not, okay, we're not talking about negatives just yet. Okay, so these two things converge. As long as they converge, then, now I'm going to explicitly write a few of these out. One, the sum n equaling 0 to infinity of AN plus BN is equal to the sum 0 to infinity of AN plus the sum 0 to infinity of the BN. Okay, now this is important. Converging series, okay? As I told you when we started this stuff, when we start playing around with infinity and having infinitely long lists, sometimes our rules of arithmetic start to fail us. And we'll see a couple examples of that maybe tomorrow. Okay, so this is something that you would just knee-jerk say to do. Well, that's if it stopped, like at a capital N up here. But the fact that we're going to infinity means that this happens, okay? And then number two, as long as it's converging, the sum n equaling 0 to infinity of C times AN, this can be factored out. Like so, okay? And then the rest of these I'll just, the last one I'll just write down. The sum of the ANs minus the BNs is equal to the sum of the ANs minus the sum of the bn's. Okay. Okay, now I'm gonna prove one of these. Like, I'm gonna prove number one. Okay. Let's let Sn be the sum k equaling 0 to n of ak, and let's let T sub n be the sum k equaling 0 up to n of the bn's. And because they converge, since sum of the an's and the sum of the bn's converge, that means that the limit as n tends to infinity of Sn is equal to S. The limit as n tends to infinity of the Tn equals T, sum St. Okay? All right, so if I was to let Rn be the sum k equaling 0 up to n of ak plus bk, well, now this is a finite list. So what we get is Sn plus Tn, because I can reorganize everything in a finite list. In an infinitely long list, you have to answer some questions before you know it's okay to do that. So we're looking for the limit as n tends to infinity of Rn, and that's going to be the sum 0 to infinity of ak plus bk. That's the limit as n tends to infinity of Sn plus Tn. Using our limit laws, we see that's going to be S plus T. And now that's the sum 0 to infinity of the ANs plus the sum k equaling 0 to infinity of the BNs. And it worked. I mean, case. Okay, so Eduardo, your junior year, you're going to have to start proving stuff like this, and maybe a couple others. All right. Now remember, when I'm doing these proofs, I just want you to try to follow them. Just see what you can follow. Okay. All right. So he has some exercises in here where he's saying, okay, determine if this series converges, and if it converges, find the sum. Okay, now, so here's the story. Finding the sum, that's a luxury that doesn't always work, okay? Every now and then it does. So if I'm looking in the exercises here, it looks like, let me try this one. Sum, my magnifying glasses aren't very good here. Let me see. What's that say? That says n equals 1 to infinity of 1 over whoops. One plus 2/3 to the n. So does this guy converge or diverge? Well, what he's wanting you to do is identify what an is. Okay. and the limit as n tends to infinity of an is the limit as n tends to infinity of this thing. And this thing goes to 0, so that's 1, not equal to 0. So that means diverge. Okay? The only ones that you're going to be able to add up in this section and get the actual sum are going to be guys that are geometric or perhaps guys that are telescoping. So, like for this one here in the book, sum n equaling 2 to infinity of 2 over n squared minus 1. So what we do is we do the partial fraction decomposition. 1 over n minus 1 minus 1 over n plus 1. So if we look at the nth partial sum, it's going to be the sum from k starting at 2 and going up to n of 1 over k minus 1 minus 1 over k plus 1. So we start writing it out here. It's going to be 1 minus 1/3. Then when it's 3, it's going to be 1/2 minus 1/4. And then it's going to be, when k is 4, 1/3 minus 1/5. Okay, so what's happening here is this guy is going to cancel with that guy. Okay, if I keep going with this, 2, 3, 4, k equals 5, 1 over 4 minus 1 over 7. Okay, and so what we're seeing here are these guys are going to cancel, right? So keep going with this. 2, 3, 4, 5. When n is 6, 1 over 5 minus 1 over 8. And now that guy's canceling. Okay, so in the next one, the 7th will cancel. Then it's going to end up being 1 over, let's say I'm at n minus 1. N minus 2 minus 1 over, when k is n minus 1, that guy. And then when it's n, it's going to be 1 over n minus 1 minus 1 over n plus 1. Okay. Now, eventually, everything is going to cancel. Okay. Except for that 1 and the half. Okay. And then this trailer piece right here. Okay. So the Sn apparently is equal to 3/2 minus the 1 over n plus 1. The limit as n tends to infinity of Sn is 3/2 minus 0, which is equal to 3/2. Okay, so I guess the moral to the story, the sum starting at 2 and going to infinity of this guy, 2 over n squared minus 1, converges apparently to 3/2. Okay, now you might want to verify all that stuff. Okay, so in these exercises, you really need to kind of immerse yourself in this stuff. I normally say 1 day on, 1 day off, but it's been a long time since I've done 185 in the summer. So just do your best, you know. It's kind of on you. There's only so much I can do. Okay. So, yeah, a lot of exercise, a lot of word problems and stuff. Number 87 starts talking about Cantor sets. So these are all for math majors and graduate school stuff, Cantor sets, but there's a lot of interesting stuff. Okay, so we'll end our review and I guess start some new stuff with a reminder of something. Result. Suppose the sum k equaling m to infinity of ak converges, and suppose that the sum k equaling n to infinity of the bk diverges. Okay, so then it doesn't matter how many new guys you put in to this guy, still converges, but to a different limit. Okay, and the sum k equaling n to infinity of the bk still diverges. Okay, so what I mean by that is this. We already know that the harmonic series diverges. So even if I start at 1,000,000 and go to infinity, it's still going to add up to positive infinity. Okay. Now, just to show you this, so like, for example, we know that when you start at 0 and go to infinity of, let's say, 1/2 to the n, it adds up to 2. Okay. Now, if I take away the first term, what I can do, now this is where we're kind of playing loosey-goosey here with the rules. 1/2, 1, so it's not sum. It's equal to 1/2 plus 1/2 squared, 1/2 cubed. Okay, now what I want to do is I want to factor a half out. Now it turns out I'm allowed to do this, but I just don't know that I'm allowed to do it yet. In any event, what you get is 1/2 times the sum, 0 to infinity of 1/2 to the end, which is 1/2 times 2, which is 1. Or you could have just subtracted off the first term, 1/2 to the 0. Could have done that as well. Okay. All right. So the removal of a finite, or the addition of a finite number of terms isn't going to alter anything. Okay, new material for today, 11.3, the integral test. All right. Okay, so let's start off with an example like, suppose I was interested in adding up n equaling 1 going to infinity of 1 over n. Okay, now we know that this equals, we know this diverges, let's say. Okay. If we look at the function f of x equaling 1 over x and graph it, and draw a better axis here. Okay, so in that other program that Tyler Booger uses, it straightens out lines for you and stuff. Okay, so here's 1, here's 2, here's 3. Okay, so let's say that this is 1. It's the y-axis, x-axis. Here's 4, here's 5. Okay, now when I plug this guy in, I get a half. This guy in, I get a third. This guy in, I get a fourth. So what's happening here is this curve is what you think it is. Okay, it's the 1 over x curve for the x being positive. Okay, and it's coming down like that. Okay, so now if I was to draw some stuff on the inside, like let's say I was to draw this box, and then this box, and then this box. The area of this box is 1. The area of this box is 1/2, right? The area of that box would be 1/3. Okay? So if I was to add up all of the areas, 1 plus 1/2 plus 1/3, these would all be underneath the triangle. I mean the guy, right? Another thing that I could do is I could, I forgot we were showing diverge here. Oh shit. Let's stop that. Do my number line again. I could do rectangles over the curve. Okay, so, oh, I incorrectly said last time that that area was 1. It was actually a half. Okay, and then I'll do the rectangle like this, and then I'll do the rectangle like this, rectangle like that. Okay, now I think we can clearly see here that if you add up all of the areas, it's going to be bigger than the integral from 1 to infinity of 1 over x dx, which we found out diverges. The sum of the areas is 1 plus 1/2 plus 1/3. So what we've got here is the sum, n equaling 1 to infinity, of 1 over n is larger than the integral 1 to infinity of 1 over x dx, which we know goes to that. So the conclusion is this sum, 1 to infinity of 1 over n, must diverge. Okay, now D'Orsimi didn't do that. We saw what he did. But we can kind of use this idea pretty much any way we want. Okay, so let's just do it in general. So suppose I've got a sequence. Let me move my angle here. So suppose, come on, man, turn around this way. Suppose we have a sequence of numbers, an, where the limit as n tends to infinity of an equals 0, and it is decreasing. So if I try to draw a picture of this guy, like this, and then like that. Okay, so here's 1, 2, 3, 4, 5, so on and so forth. Okay, so it might be that this is, and if an is, some f of n like that, then this might be where a sub 1 is. Okay, so if we were to graph y equals f of x, where f is decreasing to 0, we are going to get some picture that's going to look like this, diving to 0. Okay, it's going to be going down, down like that. Okay, and not that little tail. Going down, down, going down, down. Okay. All right. Well, what I can do here is two different things. In blue, I'm going to draw rectangles over the function. Okay. And in red, I'm going to draw them under the function. All right. Okay. So here's going to be our experiment. So suppose that the integral from 1 to infinity of f of x dx converges. Okay. Well, according to all of this stuff here on the y-axis, this is where a2 would be. This is where a3 would be. And this is a3 would be. This is where a4 would be. You guys get the idea? Okay, so the integral, if I was to add up the area of these rectangles, like if I was to take A2, the red stuff. Here, let me do that in red. Okay, red shit. Okay, so here comes the red. So the first area is A2, then A3, then A4, on and on, which is going to equal the sum for K starting at 2 going to infinity of AK, this is smaller than the integral from 1 to infinity of the f of x dx thing, which we know is finite. And so the sum k equaling 2 to infinity of a sub k converges because it's sitting underneath an integral that we know adds up to something. Okay, so that means if I add back on the first piece, we know now this to converge. Okay, now in blue, same picture. If this integral diverges, well, the only thing it can diverge to is plus infinity. Remember, everything is still positive here. Okay, we're not doing any negative stuff. Okay, well, if I look at the blue pictures, it looks to me like A1 plus A2, this is the area of all of those squares, looks like that's bigger than the integral from 1 to infinity of f of x dx, i.e. the sum k equaling 1 to infinity of ak is larger than this guy, which equals plus infinity. So that means that this sum of the AKs diverges. Okay, now this is all from the integral. Okay, so again, people have been thinking about infinitely long sums for a lot longer than a lot of us think. 1300s, Diorsimi is looking at this stuff. There is some other evidence of other things going back, to ancient Greek times and stuff. And as these things come up, I'll point out, when they were discovered, if I know, and all that stuff. Okay, so the conclusion that we've reached here is the following result. Okay, and that's our first test, and it's called the integral test. Okay, so suppose that f of x is continuous on the interval 1 to infinity. F is decreasing and the limit as n tends to infinity of f of x is equal to 0. If we were to let an be f of n, then here's what the conclusion says. Okay? Then the series sum of the ANs and the integral one to infinity f of x dx both converge or both diverge, meaning they do the same thing. Okay, we're going to have other tests with the same punchline, that the things do the same thing. Okay. So like, for example, the sum k equaling 27 to infinity of 1 over k cubed. Converge or diverge? Well, what you do is you integrate from 27 to infinity, solution here, 1 over x cubed dx. So that's going to be x to the negative 2 divided by negative 2 evaluated. Now I'm going to get real sloppy with my notation here. Okay, so that's going to be 1 over 2x squared evaluated at 27 and infinity. And so this is a finite number, because as an improper integral goes, this thing would go to 0, the end piece. Okay, so that means that this sum, k equaling 27 to infinity of 1 over k cubed, converges. Now we don't know what it converges to, but we do know that it converges. Okay, this is one I'm going to do for us later. This is what's called the Basil problem. Once people started bringing calculus to bear on this kind of stuff, it was real easy to decide, does it converge or not, just by using the integrals, okay? But this one, the closed form of this was sexy, you know, 1 over n squared, going from 1 to infinity. So this was called the Basil problem. Find a closed form for that. And it was a young Leonard Euler, of course, who figured this out. Now, he used some techniques that are a little bit sketchy. Like, he used some results about finite polynomials and applied them to infinitely long polynomials. Now, it turns out that he was okay in doing this. He was a man of his time, and when Euler's day, which was the 1700s, early 1700s, well, he's from early to late, people didn't think to question everything. Now, that being said, Euler was one hell of a smart dude, so maybe he just didn't think the world was ready yet. But in any event, this is what we have. A standard problem is going to be find all the values of P such that the sum 1 to infinity of 1 over n to the P converges. Okay, so the solution. We know if P equals 1, it diverges. So suppose P doesn't equal 1. My function, f of x, is going to be 1 over x to the P. And hopefully you guys did this problem when we were in this section, because this is always in there. The integral from 1 to infinity of x to the negative P dx. That's x to the negative P plus 1 divided by negative P plus 1, 1 and infinity. So this is going to equal, if I multiply everything by a negative, it's going to be 1 over, then it's going to be 1 minus P minus 1, x to the p plus 1, evaluated at 1 and infinity. Okay? And so this is equal to, when I plug in the 1, remember the p doesn't equal 1, but so what it is 1 over p minus 1 minus the limit as t goes to infinity of 1 over p minus 1 times 1 over t to the p plus 1. Okay, so the whole question now boils down to this. This integral comes down to figuring out what's going to happen to this. Well, it can be two different things. As long as this exponent is positive in the denominator, the limit is going to be 0. Okay, and this is if p plus negative p plus 1 p. I got the wrong exponent here. It's x, no. I got the wrong exponent. Okay. It's x to the, now this is going to be p minus, when I bring it downstairs, I get rid of the negative, p minus 1. This is going to be t to the p minus 1. Okay, p minus 1. This is going to be 0 provided that p minus 1 is bigger than 0. Okay, and it's going to be infinity if p minus 1 is a negative number, right? Because if it's a negative number, then this exponent thing goes up to the top. So that means that the integral from 1 to infinity of 1 over x to the p dx, it's either equal to 1 over p minus 1. This is when p is bigger than 1. Infinity if p is less than 1. Just solving those guys there. Okay, so the conclusion, I'll call this the p-test. No, unfortunate. K equaling any number to infinity, 1 over k to the p converges for p being strictly larger than 1, diverges for p less than 1. Okay, so that's the cutoff. All right, so like for example, if I'm looking for the sum n equaling 280 to infinity, 1 over the square root of n, that's the sum, n equaling 280 going off to infinity of 1 over n to the 1/2. So the p is 1/2 less than 1. That means diverge. Okay. Now an interesting little twist here. In a few days, I'm going to manipulate some shit and I'm going to get that to add up to something. All right. Now, it's a bit confusing once you're all over this stuff, because this is fairly sound mathematics. You know, all we have to do is have the p bigger than 1. Now, it's not telling us what it adds up to. It's just telling us that it adds up. Okay, so
Professor, when you scroll up to the second, go up just a bit. So when it's 0, if p is -1, then it's greater than 0. And infinity, if p is -1, less than 0. So it's not plus 0, right? P plus 1.
it's p minus 1.
Okay.
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 Okay, so this is all I need. Sum n equaling 1 to infinity, 1 over n to the 1.0000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000. Zero, 1 converges because p is bigger than 1. Okay? It's on the board there. No, it's marking. Okay, so let's see here. For example, the sum n equaling 1 to infinity of 1 over n to the 1 plus epsilon converges for all epsilon bigger than 0, because the p, which is going to be 1 plus epsilon, is bigger than 1. Okay, now if I start to monkey around with this sum here, 1 to infinity, just using the rules of algebra, n times n to the epsilon. Now this epsilon is supposed to be a really small number, okay? So if epsilon is a half, it's going to be n times the square root. If n is 1, if epsilon is 1/3, and so on. Okay, now, last semester when we were doing L'Hopital's rule, I gave us this characterization that if you were to graph all of these rooting functions, cube root of x, fourth root of x, and so on and so forth, sitting down underneath all of them is y equals the natural log of x. Now it might be, if I blow the picture up, it might be that one of these rooting functions hits it, but then it will eventually go past it, the log, and we were able to show this by L'Hopital's rule. Okay, so the limit, I guess, now this is not, I can't really say this legally, but the limit at, well, legally, yeah, legally, as epsilon goes to 0, I mean, as epsilon goes to infinity, well, wait a minute. I'm going cube root. Well, the limit is n tends to infinity of the nth root of x, turns out to be the natural log of x. Okay, so maybe what we'll do is we'll put the thing that's underneath that and see what happens. So the question here is, if I put the logarithm under here, is that enough of a bump for the denominator to get big enough so that this is going to add up to something? And of course, we have to start it at 2. So what we'll do is we will integrate it. F of x equals 1 over x log x. The integral from 2 to infinity of 1 over x log x dx if u equals log du is that, okay, so u is the log of x du 1 over x dx. Okay, no matter how you want to look at this, what we're going to get is the natural log of u, which is going to be the natural log of the natural log of x, evaluated at 2 and infinity, which is the limit as, let's say, t goes to infinity of the natural log of the natural log of t minus the natural log of the natural log of 2. Well, sorry, gang, but that's still infinity because the logarithm is still an increasing function. Okay, so this was not enough of a bump in order to get it to work. All right, so he's kind of going all through that for you right there in this section. All right, let's talk about error. Okay, so for a sum, for a series that converges, let's suppose that the sum of the AN of the AK converges, okay? So maybe let me write out specifically. K equaling, maybe I'll start it at 1 this time. Doesn't matter where we start though. So this thing converges, okay? Now what we do is we use Sn to estimate S, which is this sum to infinity of AK. All right. So just to give away a little secret here, there are infinitely long polynomial representations for all of your functions that aren't polynomials. Square root of x, logarithm of x, sine, cosine, e to the x. What our calculators are doing is they're plugging them in to those polynomials that have been truncated at a certain spot. Sort of like we're saying that this Sn is going to approximate this. So what we're interested in is figuring out what the error of approximation is. Okay. So let's draw a little picture here. Okay. And I'm going to go out where we've gone out quite a ways. And here's where n is on the axis. On. Okay. And I put a little, in there like we've come out quite a ways. Okay. And then here's like n. And this could be like n plus 1. Okay. And then maybe this could be n plus 2. Okay, now again, if my function is coming through these points, he's kind of sweeping down. That's a little too linear. Okay, so it's coming down like this, coming down, coming down, coming down. Okay, so if S is equal to the sum k equaling 1 to infinity of ak, then this is going to equal Sn plus the sum k equaling, go to the n plus 1 to infinity of the ak. Okay, so obviously here, the error is going to be this leftover piece. That is the piece that we're missing. Okay, so if we draw some guys here, like I'll draw some red guys over this guy. And then I'll draw some blue underneath it. All right. What we can say here is the area of this guy is the area of the blue guy is A sub n plus 1. The area of the red guy is A sub n. Okay? Okay, so if we were to look at the integral from n plus 1 to infinity of our f of x dx. Okay. So I'm integrating from here. Okay. This is smaller than this thing, where I'm going to go this is where he kind of has a little bit of a hitch in his notation, so I'm going to try to fix this real quick. Okay, so if I was to integrate from n plus 1, here, let's start this over. My dogs suck. So let's see here. Okay, so what we're going to do is we're going to say, let's let Rn be this sum, the rest of it, or the remainder, if you like, plus 1 to infinity of ak. Okay? So the integral from n to infinity of this f of x dx, which is the area underneath the curve, okay, this is larger, right, than a sub n plus 1 plus a sub n plus 2, which is the sum k equaling n plus 1 to infinity of ak, which we just decided to call r sub n. Okay, so what we've got here is that r sub n is smaller than this integral, 0 to infinity of f of x dx. Okay, now he also has another side to this. He also says that n plus 1 to infinity of f of x dx is bigger than Rn. Or wait a minute, less than Rn. Okay, let me just write down in the thing what he says. Okay, in the book, here's what he writes down all at once. Forget this shit in a second. So he does this. Now all you have to do is look at the pictures. Okay, so the integral from n+1 to infinity of the f of x is less than or equal to the Rn, and the Rn is smaller than or equal to this guy. Okay. Okay, now the integral from n+1 to infinity. So it's going to be all of these blue guys. If I go n+1 to infinity, the Rn, which starts with the an+1 box, is not larger. Okay, so this needs some adjusting, but this spot is valid. Okay, so as he draws these pictures, he's clearly like jumped the gun here with something. He says, similarly in figure 4, we see that Rn is an+1. So he's using, oh, I see what he's doing. Okay, now I got it. Okay, so let me get another color. How's about green? Okay. So now what he's doing is he's doing this, where he's starting here. What was I going to do? Green? Okay. So he's doing these boxes in green. Okay. The area of this box is also an+1. Okay. So I think we've now explained this guy. Okay. But it's this piece that we want. Okay. So let's do an example of this. Okay. So for example, let's say I want to estimate the sum n equaling 1 to infinity of 1 over n squared with s sub 10. Okay, so that's going to be 1 plus a fourth plus a ninth plus 1 over 100. Okay. All right, so I'm going to do that on my calculator real quick. So calculator, sideways. 1 plus 1/4 plus 1 over 9 plus 1 over 16 plus 1 over 25 plus 1 over 36 plus 1 over 49 plus 1 over 64 plus 1 over 81 plus 1 over 100. So what I have is that S10 on my calculator is roughly 1.5497677. Just keeps going. Okay. Now the Rn, the error piece, this is going to be less than or equal to the integral from 10 to infinity of this 1 over x squared dx. So what that is, it's going to be 1 over x evaluated at 10 and infinity. Remember, that's x to the negative 2. That integrates x to the negative 1 over negative 1. So what we get is 1 over 10, which is 0.1. Okay, now, remember that I know what this sum adds up to, and I can actually do it several ways. Okay, I'm going to give you guys the way that you'll understand. You need complex analysis to understand the other ways. You need Fourier series to understand that another way. Okay, so if I take pi and then I square it, equals, what didn't happen? Okay, take pi, where's my pi by? Square it, okay, and then
9.86.
divide by 6. What I get is 1.6449340 ... Okay, so if I look at my error, if I take the absolute value of S10 minus the R10, I mean, not that, the error in the actual sum, pi squared over 6, take this, take the two numbers and subtract them, 1.5497677, and I subtracted the wrong number. Okay, start over again. So I get pi squared divided by 6. I'm going to subtract off 1.5497677, and what I get is 0.095, and that's certainly less than 0.1, just as advertised. Okay, now the nice thing here is that we didn't have to know this to guarantee it. This is yet again another one of these places in math where, and here it's not concealed. I mean, it's all in the picture. Back with the Simpsons rule and the trapezoid rule and all of that stuff, I had to kind of tell you, well, I can show you all this, but it's going to require a little bit more math. Here, it's solid. It's all there. Okay, and it's all done with these rectangles. You can also use this to decide how far out you want to go. Let's say that you want your tolerance to be, let's say you want your error to be less than point. I have my screen up now, that's why that looks all weird. Okay, so what you do is just throw the n in there and you deal with it. Okay, so he's got a few of those problems. Okay, so this is 11.3, and of course, it's going to be, surprise, surprise, a whole bunch of integrals for you guys to do. Okay, so hopefully you can kind of see why I wanted you to integrate so much, because we keep having to do it. All right, so this is kind of the pace I kind of want to go. Tomorrow I'm going to look at a little bit more of this. Number 33 is the zeta function, and I'll do my usual, what I do in Math 185 is I always review what we did the day before, maybe a problem or two, and then move on to some new stuff. Now you guys really have to actively get in there. There's going to be results in your head that need to separate. We're going to have one result about a series that says, okay, as long as this limit is positive, it's going to converge. Then we're going to have another result that's going to, different test, that says, okay, if this limit is bigger than 1, it converges, less than 1, it diverges, equals 1, we don't know what it is. Now, this takes time to separate in your brain, you know, like other things, you know. So doing lots of problems, I mean, that's just the way I see it. I mean,
Somebody just asked if it was going to be on the exam.
on the next exam, I am going to put a few of these guys on here. Does it converge, yes or no? Just because I want to get you engaged. And I can get in the chat now. So there will be one or two. I mean, I don't know. I haven't made the test yet. Trying to challenge you guys with, you know, these problems. Didn't seem to challenge you too much on the last exam. Like I said, I really challenged my Math 30. But then again, I could put a test out that, you know, here's what I'm gonna do on their next test. The answer to number 1 is gonna be 1. The answer to number 2 is gonna be 2. You get it? Okay. Let's see if they pick up on it. I had a high school teacher that he would give us these multiple choice exams, and it was a history class, and the key ended up being Mickey Mouse and Goofy. And so once I used to do statistics, you know, a long time ago. I haven't done stats in 20 years. And I got so sick and tired of people arguing over, you know, well, I'm only 0.001 away. Well, it's, you know. So what I did is I made all my tests multiple choice, and I went through every possible wrong thing they could do. But I always like to leave a none of the above. And I had this one class at Saddleback that just pissed me off. I just hated these guys. Made my life so difficult. So on one of their tests, I made every single answer none of the above.
Oh my God.
So,
So screw with them, man.
yeah. Give your professor a hard time, man. Sometimes they bite back.
I had a professor at Saddleback one time. He made it, you know, the scantrons? When you bubble them in, he made it where it was like diagonal. It was just doing this. And then for the final, he had one where it was just like it was
a math class?
Yeah. He had the scantron where if you flip it sideways, it said something like a small message.
Do you remember who it was that taught it?
I don't remember. I think it was a science professor. It could be an algebra professor. Both of them were crooky and they both sat together.
I almost got hired there. I was so close. I made it to the president's interview in '98. And you know, my Saddleback had a real problem. They only had 2 women in the whole department.
Wow. And
so there was this girl that was applying. She was one of the hot candidates, Lisa Silvera. She's still there, I think.
Yeah.
And the person that probably helped me the most in getting my jobs and all that stuff was this woman named Karen McClure. She was the scheduler at Santa Ana College, and she was just blunt and honest with me. So like I would ask Cheryl Uden, like, so how come I didn't get an interview? Like, what separates this person from me? You know, and she'd put her arm around me. It's okay, Bobby, it's gonna be nice. It's okay, you keep working. I asked Karen the same question, and she'd go, oh, okay, okay, so you suck. Let me show you why. That's what I needed to hear. Okay. Yeah. And so I applied to Saddleback. I think I got a courtesy interview because a guy was driving to school on the first day to teach a statistics class and had a heart attack and died. Oh. And so Jean Smith, the chair, she desperately calls me and says, can you do this stats at noon? And I'm like, sure. And so I did it.
That's a bummer.
And I think that's why they gave me an interview. But when I got an interview, I went to Karen. This is my first interview ever. Karen, I got an interview. She's like, Bobby, you're not getting hired. They have to hire a girl. It's this. And back in those days, Saddleback was all in the news. they're chancellor of that district, South Orange County. The chancellor was teaching a class at IVC, which is in the district, about how the Holocaust was fake and never happened. I mean, this is, yeah. So these guys were just in the spotlight. And then I got a president's interview, and I go, Karen, man, I got Bobby, you know. So, you know, I didn't get hired, which was very deflating. But anyways, I liked it down there, South County, you know.
Worked out well in the end, man. I think OCC is like a higher ranked college than Saddleback by far.
We don't get paid as much, though.
Really?
Saddleback is the highest paying district. Santa Ana is very close behind them.
Oh, okay.
We're one of the worst paying districts. I think to get lower than us, I think you got to go to Barstow.
Oh, wow.
But see, we don't have Melrose.
I don't understand.
So Melrose is like if you buy a house in Aliso Viejo, it's an additional property tax.
Oh, kind of like an HOA fee?
Yeah, but what the Melrose does is it funds things. So it'll fund sanitation, it'll fund your local college. Okay, well, where I live, you know, Brian, you lived around here. These are old homes. There's no association, no Melrose.
Yeah. Property
taxes were frozen by Prop 13 a long time ago. So we don't have the kind of funding that other districts have. Santa Ana, for example, they're on an entirely different kind of funding system because of their population. During the day, it's largely Hispanic, and at night, it's largely Asian. At least that's the way it was when I was there. And so they get different kinds of funding.
But what I don't get is OCC has way more students than like Santa Monica, but then a lot of these other schools. Shouldn't the tuition also go towards something?
Your tuition, the model, the initial model was, it was all supposed to be free.
Okay.
And then it was decided that, okay, that's a bad idea.
Because people don't show up.
Well, they're going to have some skin in the game, you know?
Yeah. And
so the fees are even the fees that you pay. How much did you guys pay for this math class?
Two something. I think two.
Right. So to take this class at USC
it'd be insane.
Yeah, it's going to be like $12,000.
Yeah.
But even to take this class at a community college in Arizona is going to be several $1,000s.
Really?
So, yeah, keeping the fees low is something that the state has really tried to hold on to. But still, you know, they go up. Now, for every dollar that you pay in fees, the state probably kicks in 200.
Oh, okay.
So it's a lot more. So your fees don't really cover a whole lot.
Oh, okay. I thought the fees would actually do well because if you had 200 people, 60 students, yeah, I mean, it's not like it's nothing, you know?
And I'm pretty sure, well, if you dig around hard enough, you can get out of paying your fees.
Really?
Oh yeah, my wife, she got our son Tyler. He didn't have to pay first year at OCC. They have there's all these programs that you just gotta reach.
Yeah, like the BOG and a bunch of other stuff, but
our counselors aren't very good.
Yeah.
And so, you know, they don't let you know these things. But there's ways to get your fees waived.
I mean,
Tyler even got paid. They even gave him $50 a month.
Yeah, no, I got that when I was getting my undergrad too. The FAFSA, the BOG, all the other junk. But yeah, I mean, it's still like there's a lot of people who aren't getting that. And I assume the government chipped in some, but I was assuming just the tens of thousands of students that went to OCC were actually.
There are so many scholarships every year and fellowships that don't get claimed.
Yeah.
Like, for example, if you are a direct descendant of a World War I veteran, there's some money for you. Now I am, and I can document it. But back when I needed to document it, I didn't know that that was a thing.
Yeah.
I'm 1/64th Native American.
Oh, okay.
But I can't document it.
Oh,
But if you look at my granddad's face, I mean, you see it. And
Okay.
Mother Hawkins, his mother,
Yeah.
like she was the baby of the girl who got kidnapped by the Cherokees and then brought back with a
Oh.
baby. So you
Oh.
see it in their face. It's very profound.
Oh, okay.
And there's a fellowship out there that's actually a lot. It's a graduate school one.
Oh,
And as I was leaving UC Irvine, this guy was coming in. He was from Florida, and long hair guy like me. We start talking, and he's like, "I'm on a fellowship. I'm on the Native American fellowship." I'm like, "I could have done that too. I just can't document it." And he
Yeah.
said, "I didn't document it. I just told him."
Yeah.
And I'm like, "Shit."
yeah. And
But
I
if you
got,
dig around out there, there's stuff.
no,
you know.
I got one of those. Some of the teachers sometimes like push you for them. Like I got a music scholarship or a music whatever award. You know, the award nights that they have. My wife got a bunch of those too. I mean, they're cool, but I don't know. I honestly like. I just now that I'm not in undergrad anymore, it's just a bummer because when you're in undergrad, if you know the right systems, I mean, yeah, school's free and they pay you to go to school unless you're crazy, crazy wealthy. So yeah, but it's just a lot of people don't know how to look into that, or they don't qualify if you're not from here and things like that. But it's
I think that the counselors at Costa Mesa High School are really good
Hmm.
because they are really trying hard to get that population into college.
yeah,
You have a lot of first generation, born here, parents are immigrants, stuff like that. And they have done such a good job that in this school district, Costa Mesa High School is now number 2
whoa,
behind Corona Del Mar.
oh
And
wow, what happened to Newport Harbor? They totally dropped the ball.
Well, I mean, they're still in 3rd, and then Estancia is in 4th, but the Costa Mesa people seem to be on it,
Yeah,
from what I was hearing from some people, like, CDM has a really bad heroin problem or opioid problem going on over there.
Hmm.
And, but the Costa Mesa people are very motivated just because of their population. The population is CDM and a bunch of rich white kids.
yeah, no reason to care.
And their parents are going to figure out a way to buy them into USC and, do all that shit.
They don't
So-
really need to go to school.
No.
They will find a way. Yeah, man, it's a weird thing. But yeah, it happens. It's great for some people,
Ask mom.
but yeah, just like I was talking to one of my buddies saying, he's like, what do you pay for rent? I told him, he's like, oh yeah, my dad, and I didn't realize this, but he's like, my dad's trying to rent his 3rd home in Long Beach, and they want to rent it cheap to someone they know. But I mean, it's a home. Like it's a home with like a jacuzzi and a pool. And it's like what I pay for a 1-bedroom apartment in Costa Mesa is going to be, even if they like me, nowhere near what they'd want for like a 3-bedroom home in Long Beach. Has all this stuff. So some people just like their parents set them up to a place, like his parents just bought him a house in Texas. Their parents, and then they're buying another house in Texas for the whole family. Their parents set him up like to a place where it's like, crazy. And my parents could have done the same. My dad was extremely frugal. So it's, just he never wanted to buy. Like, the big clock house, they were going to buy their neighbor's house too, and then just turn it into a second house. Because, I mean, houses cost nothing back then. My dad bought their house for $50,000. So
Yeah. I've seen the original layout here. When we did the addition, I went into the city.
Yeah.
And all these lots have been pretty much cut in either half or 4s. The
yeah.
original lots, they were all spaced out as big rectangles that alternated like this.
Yeah.
And this whole area used to be tomatoes. That's why we have all the ants.
It's crazy, man. Like, did you know where the Vans house was on West 18th?
You mean the toes on the nose place?
No. So like there was a house on West, I think it was West 18th. Yeah, West 18th. And it was taken over by Vans, like the skateboarding company. And then they turned into like a skate park. They emptied out the pool and they turned that
I think that's now the toes on the nose place.
It became actually like a bunch of townhomes. Like
Oh,
became
okay.
tons. Anyways, it was 2 acres of property over there on West 18th. Like that's my grandma's house. Like that's what she had. So like, yeah, property used to be nothing, man. my grandpa, when he passed away, had 2 families, so it had to be divided. But he owned 10 different properties, 5 in California and 4 in Mexico and a couple in other states. But it's like, yeah, just property costs nothing. You know what I mean? If you had some money. But nowadays, it's like people are extremely lucky if they're able to buy a house. Like, I don't even know what people 5 years from now are going to do if this housing market doesn't crash hard.
No, it's not going to crash again.
Has to, man.
I think all of that has been corrected. No, what you don't have are these credit default swaps going on. See, that's the thing that did it. It was all the credit default swaps, and the people that got stuck holding the bag at the end was AIG. They held all of the risk for all of the credit default swaps.
That's
and
why
if
the PMI
AIG goes under, the entire world goes under. So now, with all of this new TARP legislation and stuff that all happened back, there's a really good movie on it called Too Big to Fail.
Yeah,
I've heard of it.
Yeah.
that was amazing.
So all of that speculating, I mean, these banks were trading, they're basically commercial. So they were investment banks, and then they were being traded themselves,
Okay.
you know, and then they start buying up. I just saw something, somebody's trying this up again. Charles Schwab, he said, hey, if you don't have enough money to buy a whole bunch of Apple stock, how about you buy this product? And they have a bunch of percentages of stocks of like Apple and Amazon and whatever. And that's a product that you can buy. But what was happening was the product was all of these mortgages that were going out. And to people that, you know, basically when the teaser rate ran out, they defaulted. They try to sell, the housing market goes down. See, here's my theory.
Okay.
This all started with Bill Clinton.
In the 90s.
Bill Clinton, say what you want about the guy, you like him or not, the dude is smart. Okay. He gets very lucky. If it hadn't been Ross Perot in that race, he doesn't win the presidency. So Clinton comes in, he loses the majority in the House and the Senate right when, you know, after that, the first 2 years.
Yeah.
So what he starts doing is he starts throwing all the Republican stuff at the Republicans. So he gets Greenspan to just keep lowering that federal interest rate, and people then start taking second mortgages out on their house and buying a boat, buying a new thing and whatever. Okay. And then that just kept going and kept going. And that was the culture. And then Bush becomes president, and it just keeps going. And then out of nowhere, one day, Goldman Sachs can't make their responsibility in the morning, and so.
Well, you watched The Big Short, right? I like that because it's a really fun retelling of that whole story. You saw that movie, right?
Yeah.
I've seen a bunch of shows on it.
No,
I like the frontline ones, the ones with all of the. When is the next exam?
Probably tomorrow, right?
No, I said probably Wednesday
I was late to class.
or Thursday. Yeah, because I want to be able to put some of this material on it.
Will it be like the same assignment, or will it be timed within 2 hours?
It won't be timed like the first one, but I'll make it available and, you know, give you like 24 hours to do it or something like that. But I want you doing stuff in addition, you know, to these, to the problems that I'll be assigning to you.
Well, next time you get a chance, man, if it's on any streaming services, watch The Big Short. I mean, it's a movie. It's not like a documentary, but it's a really fun retelling of the housing market crash in a really, really well-educated way. Guy who made, it's not Hangover. It's the guy who made like The Other Guys and Anchorman. He made it. And it's got like Steve Carell and Brad Pitt and Ryan Gosling, all those people are in it. It's really good, and it's a
Probably
really.
on Prime, Amazon Prime Video. Let's see.
I don't think it's on there. It was on Netflix for a long chunk, but now it's not on anything. I don't think. It's a huge movie. It won a bunch of Oscars and stuff. But it's an easy like to follow retelling of how they destroyed the stock market by like selling subprime loans and selling AAA bonds to all these people and selling homes under. Do you know the ninja loans? No interest, no charge, no asset.
Yeah, there it is, right on Amazon Prime, or on Prime.
I don't think.
Yeah.
I think you have to pay for it, man. I don't think it's free if it's on Prime. Like I don't think it's a Prime Video. Yeah, it's not. It's like a.
Well, you only have to $3.99.
Yeah, whatever. I mean, yeah. If you ever get a chance, check it out. I loved it. My dad is like really big into this stuff, so I got it for him. And he loved it. Like it's so well made and so put together perfectly, and it's just an interesting story. Truthfully, like there's a lot of people who lost a lot, but if you're removed from that, like I personally didn't know anyone who lost anything at that time because I was going from high school to college, and my parents were in their 60s, so it wasn't like they were they were already set up. But yeah, if you're not connected to anybody and you don't have a lot of loss in there, it's just so crazy to watch so many ridiculous decisions get made, like, hey, sell people homes who don't have the money to buy them. And the one thing they leave with at the end of it, without getting too much in the movie, is that like, and the movie was made in 2016 or 2017, is they started doing that again, like about 5-6 years ago. So I don't know, man. I personally think another crash is going to happen. I could be wrong though. I probably will be wrong. Hopefully I am wrong. Because
You know who got it right was Art.
Art?
So
like
yeah,
the math teacher?
Art Moore.
Oh, okay.
Right
buy house
before,
right then?
So right before the big collapse, he sold his house in Long Beach
Yeah.
for a shitload of money.
Yeah.
And rented an apartment, and then the market crashed. and then
he bought again,
and
right?
then so he had all his money.
Yeah.
And so then he was able to buy a new house on the cheap.
Man, I had one friend I met at OCC, and his whole thing is all he did is he owns 3 homes. He lived at home, worked for Blizzard, bought a home, rented it, bought it. I probably talked about him before, because I was like, when I met him, like I was late 20s, he was late 30s, and I was like, this is the coolest story I've ever heard in my life. But yeah, if that ever happens again, and you have the capital, or anybody has the capital, I mean, that's literally what people can do as long as they have property ownership, is like just manage that property, because people always need a place to live.
We had a place, that Newport Riviera down on kind of Santa Isabel and Santa Ana. I love those townhomes.
Yeah, that sounds really. I mean, I live on Vanguard Way, Santa Isabel. Once you cross Newport Boulevard, the Newport Riviera name sounds familiar, but I'm not.
So if you drive on Santa Isabel and go towards Orange,
yeah,
you start seeing like it's like a bunch of duplexes, and we had one of them, and we sold that to buy this house, and that was the dumbest thing I ever did.
Oh, I
could've-
know Newport Riviera, man. I love those places. My wife and I always hope that they're gonna. I mean, it'd be way out of our range, but we always hope we're gonna see a for rent sign like near there, so I could call. It's right by the back bay. I go.
Yeah,
run there
we had a big open. We didn't have a open. Some people, the living room has vaulted ceiling, but you can like close it off.
Yeah.
Put rooms up there. We should have just kept that. I could have been renting that out to UCI students.
Oh, dude, you would have
for
made
probably
so much money.
$6,000 a month, and the mortgage was $1,300.
Oh man, I don't know if you would have got 6, but you could have easily rented it for 4. Like no, yeah.
Oh, I totally could, because of the number of bedrooms I'd have put in it.
Yeah.
I would have done the top floor, and then I would have put 3 additional bedrooms to make it 6.
And you should have done what the person did. My first apartment in China, when I moved over there, the night I got there, I was working for this school, and they had set everything up. I walk into this place, I'm like, I have no clue what's going on. And it's like this weird empty room we walk into, and then they show me this door where I sleep. Later, I ended up making a buddy with a Brazilian dude, and he showed me what the floor plan normally looked like. And the previous owners turned the kitchen into a bedroom, turned the living room into 2 bedrooms. They had rented the main bedroom for me, and then there was a small closet. Yeah, so they had 5 bedrooms in this place, and there was a middle centered area that nobody used because it was awkward because we were all strangers. I was only there for like a month before I found my own place. But yeah, I mean, that's what some people do, man. Like you can make a ton of money if you get a place like UCI. And one of my wife's friends was from China, and she rented a living room she was going to UCSD, and she rented a living room space to sleep in, and she still spent like $800 a month on that. And that wasn't even the bedroom. It was like the living room that people had to walk through. So yeah, it's insane what people pay. My buddies turn their garage into an apartment and rent it for $1,300 to Chapman students now. It's like maybe 350, 400 square feet. It's insane. Crazy. We're living in weird times, man. So,
How long have we been in this lockdown now? We've been 1 week.
March.
This secondary lockdown since
the new one. When did Newsom get pissed off?
Last Monday was the everything closed day.
Okay, so we have another week of this stuff, and it has to.
No, it's going to be like a month, man. I mean,
Okay,
I'm hoping.
So I'm sure this is being proposed all over the internet. How about we all just stop getting fucking tested?
Yeah.
How about that?
Well, they said that already, and people got really angry, man. You can't ask people to stop doing that, man. You can't ask people to forget or to live a normal life or to go outside or to not be angry or to do anything. It's not going to work. And unemployment, like the big unemployment ends here, I think either this week or the end of next week. And they're expecting, since it's about 20 to 22% of people are unemployed right now due to this, they're expecting a lot of people won't be able to pay their bills like immediately. I read something where it's like most people live on a paycheck where they can live for 1 week after not working before they lose all their money. And so that's like, I forgot how many, I think it's 70% of people in America live under these crazy no savings circumstances. And so, yeah, man, we're entering August. They're kind of come out with a bunch of new bills. We're going to find out what they do. I don't know. The whole thing's crazy. I'm going to try to like jump on that.
CIF today said no sports until at earliest December.
That's
so
crazy.
If there's no football, I'm going to talk to our 17-year-old like, dude, if there's no football, why don't you just take the GED and start taking classes at Coast? I mean, the only reason he's there is to play football.
Yeah, just do that. Get like some job at a grocery store while he lives at home with you. Put aside some.
He's delivering sandwiches for Jimmy John's.
Oh, okay, cool. Yeah, I mean, like, just when I lived at home, I always had a job after like 17. I'd had like one summer off senior year, but like it's good. You make some extra money. Your parents take care of your bills, but you have to pay for all everything you want to spend, right? If you guys are able to afford that,